Today we are covering lesson 6.4, vectors and dot products. So first off, what's a dot product? Now be aware that dot products basically are the x value times the x value, the y value times the y value for two different vectors. Okay, right? So u equals u1, u2, where u1 is our horizontal movement, u2 is our vertical coordinate, or motion, how much we're moving up and down. v1, v2, then horizontal, vertical, and the dot product is u1 times v1 plus u2 times v2. So our answer is going to be a number. So I say C, like it's going to actually be a value, not a variable, not a vector, a scalar number. So here are some quick rules about properties of the dot product. We have three different vectors, u, v, and w. Order doesn't matter here, is what that person says. U dot v is the same as u dot u. Multiplying by 0 would get anything 0. V and w, if you add two vectors together first and then do the dot product, it is the same as if you distribute u in. So we've got u times v, u dot product, plus the dot product of u and w. Okay. Next, we've got the dot product of v and itself is equal to the magnitude squared, which again would equal v1 squared plus v2 squared. Right? Instead of square root, since it's squared, we don't have that square root anymore. Lastly, a constant times the dot product is the same as we multiply the constant into one or the other, not both. Right? So you think about it as 3 times, say, 8, right? You wouldn't get 3 wouldn't go in twice. Right, if you think about the dot product as one number. Orthogonal vectors are vectors whose dot product is 0, and they are also perpendicular. We will use this later this lesson. So, finding the dot product of u and v. So, multiplying these out, negative 5 times 3 plus 2 times 4 gives us negative 15 plus 8 is negative 7. That simple. Next, negative 3 times 3 plus negative 2 times 4, right? And we get negative 9 plus negative 8, which is negative 17. Pretty straightforward. Moving on. Next, some of these are just to kind of get you in the practice of understanding, are we going to have a vector left over? Are we going to have a scalar, just a number? Or what's going to be left over? So again, we've got u dot v dot product times the vector w. So a number times w will be left over with the vector, is what I'm expecting. Number 4, 2 times the dot product. This is also a number, so I'm guessing we'll be left over with just a number. So we're done. So let's go ahead and process this. U dot v. We got 3 times negative 2 plus 2 times 5. So negative 6 plus 10 is positive 4. And now we're going to bring w back in. Positive 4 times negative 3, negative 11 is negative 12, negative 44. Next one, 2 times the dot product of u and w. 3 times negative 3 plus 2 times negative 11 gives us negative 9 minus 22. 2 still on the outside. Gives us 2 times negative 31, which is negative 62. So a number, and then on the left side we had a vector left over. As the more math you do involving dot products and vectors, the more understanding you will be of what type of answer we are to expect from dot products and vectors. Next, dot products are used on that formula cheat sheet I handed out to you. We're finally getting into the rest of that. We're not going to finish it today, but we're going to get into a couple more on this. It's kind of line 2. So angle between two vectors is found, right? If theta is the angle between two non-zero vectors, then u and v, then cosine theta equals the dot product of u and v divided by the magnitude of u times the magnitude of v. Now, using your calculator, a lot of these things, like if we find the dot product, we find the magnitude of square root of 26 here, the magnitude over here is square root of 50. Even though the square root of 50 can be simplified, we are doing cosine inverse of these. So just leave it in your calculator will figure it out. And then another note is make sure you're using parentheses so that your calculator doesn't get things messed up. Because often when you're doing square root times the square root, if you don't include a parentheses, it will think one of them is in the numerator. So be careful about that. Find the angle between the vectors. We've got, again, we need to find the dot product over our magnitude, and then we'll do cosine inverse over dot. So dot product, u dot v is 2 times 0 plus negative 5 times 2. When they're nice in a line like this, it kind of seems like they're right in a row. So we've got 0 minus 10, this is minus 10. Now, reminder, magnitude is the number squared, right? So 2 squared plus 5 squared, 4 plus 5 is, 4 plus 25 is 29. Next, 0, 2, what is the length of that vector? It's going to be 2, right? Just to show you, 0 squared plus 2 squared, square root of 2 squared is 2. So, right now we've got, there's our dot product down here, and continue down here. Negative 10 over 2 square root of 29, kind of flip the order around just to make sense, equals cosine of our angle. So cosine inverse of that will give us our answer. So I've got cosine inverse of negative 10 over, again, don't forget this is all in parentheses, gives you 158.199. Next, we've got cosine of 5 pi 6i plus sine of 5 pi 6j. V equals cosine of pi half I plus pi half j. If you haven't seen this before, you're probably freaking out inside a little bit, thinking you've got to go back to that unit circle. Remember, this is the vector form of cosine theta, or you can say I, and then magnitude times sine of theta. So we just need that this theta is 5 pi 6. Down here our theta is pi half. So the angle between them, we can, instead of dealing with the dot product, just do 5 pi 6 minus pi half. We need thirds, or sorry, 6. We got 5 pi minus 3 pi all over 6 gives us 2 pi 6, which is pi thirds. There's our answer. A little bit shorter that way than dealing with the dot product. Coming up next, we've got vector components. Again, it's a little bit hard to explain, but reading through this, okay, we've got two vectors, u and v, such that u is going to be broken up down into two vectors, w1 and w2. w1 and w2 are orthogonal. Well, again, this means they're perpendicular. Why would we want to break something down into perpendicular parts? Again, a lot of this has to do with gravity and force. You're going to read part from the book that explains pretty well. So we're going to read through this definition first. So again, we've got u broken down equals w1 plus w2, where they're orthogonal, and w1 is parallel to b. Again, these are other vectors, or scale and multiple of these, right? As shown in figure 6.4.1. So I think those are the figures attached here. The vectors w1 and w2 are called vector components, right? It's basically what u is made of. And the vector w1 is a projection of u onto v, denoted by right here. Now this is a formula on our sheet covered down here in the next box. Now if we know what w1 is, and we know what u is, right? If we have these two pieces, how hard is it to solve for w2, right? Subtract w1 from both sides. If you didn't see that, they did the math for you. w2 is u minus w1. We'll go through one of the simpler problems with it and one of the more complex. Next, projection of u onto v. This is where the dot product comes in again. So the projection of u onto v is given by the projection, again, it's got v in kind of a sub-letter there, of u equals u dot v, dot product, over the magnitude squared. Again, this is going to be not a square root, a squared plus b squared, right? We don't have the square root anymore with the squared times the vector v. That's why it's always going to be a scalar version of v. That's in the formula. Okay. So again, examples are kind of like shadows. A lot of our problems are going to be like we're going to have kind of an incline where they're going to give us the angle here. We're going to have some sort of weight where it's force is pulling us straight down, right? And then we're going to have, based on decline, for say right here, we're going to have W1 kind of wanting us to pull us down the decline. We'll have a force based on the weight of the unit. And then W2 is going to be this vector here from the end of W1 to where F is. And that's going to be what we're going to be solving for, a combination of those. So, moving to the next one. Find the projection of U onto V, then write U as a sum of its two orthogonal vectors. And this is W1 plus W2. Okay, one of which is projection of V onto U. So U is 3, -5, V is 6, 2. Plugging it into the formula. I'll write the formula one more time here. V onto U is, again, dot product of U and V. I already want to start multiplying here, sorry. Dot product over magnitude of V squared times vector V. So again, looking at that number, in parentheses is going to give us basically a fraction. V is going to be a vector, so we're basically multiplying V by a fraction. It's not always a fraction, but in this case it will be. Okay, so plugging it in, 3 times 6 plus -5 times 2. I got 18 minus 10 is 8. On the bottom, V, 6 squared plus 2 squared. Sorry, I should show math. 6 squared is 36, 2 squared is 4. 36 plus 4 is 40. This is what that is. Times V, which is 6, 2. I'm going to simplify a little bit here. 8 40th is 1/5. Those are the numbers we got. When we multiply here, we get 6/5, 2/5. This is vector W1 of U. Right, so we broke down U into W1. And again, just a quick note, they have different directions, right? If we looked at this as slope for a second, y over x, our slope was -5/3 there. Looking here, just for a second, our slope is 2 over 6. The fifths cancel, which is 1/3. Checking the slope of our next one, again, just to kind of give you the idea, where is it, how do we know it's perpendicular? Our final numbers will have a slope of -3 in order for this to be orthogonal, perpendicularly. So next, we've got U equals W1, and we need to find W2. So going back, taking this 3, -5, and subtracting, sorry, not a point, vector, subtracting 6/5 and 2/5. Okay. Now, I like my fifths, so I'm going to write 13 as 15/5, -5 is -25/5, over 6/5 and 2/5. And W2 equals 15 minus 6, you get a minus, and then start subtracting to get 9/5, 25 minus 2 more is -27. Now if I did y over x components here, -27 over 9 is -3. As I said, this would be, so it's kind of neat that we can break down one vector into two perpendicular portions of it. And so U equals, I'm going to write my answer here, U equals 6/5, 2/5, plus, space, of course, 9/5, -27. That was what it wanted us to write it as a sum of its two vectors, W1, W2. And W1 is that projection. Now that seems a little straightforward. Now it's going to get some real-term aspects. So I'm going to read from the book. I know it sounds really boring, but just to give you a better idea. Again, you've already seen applications in which two vectors are added to produce a resultant vector. Many applications in physics and engineering pose the reverse problem. We're trying to decompose a given vector into a sum of its two components. Okay. Now going to the last picture that I kind of talked about. I didn't draw the third one. W2 is actually kind of comes down this way. I didn't draw it quite well, so we're looking for where these two vectors are going to come into play. But getting into the problem here, right? Again, an example, consider a road on an inclined ramp. This example, we're going to deal with a truck on a ramp. So it's a pretty common type of problem. So a truck with gross weight of 30,000 pounds departs on a slope of 8 degrees. So I'm going to draw it out real quick. Not to accuracy, but it's out with 8 degrees, right? we'd have, again, W1 would be the weight pulling down the slope force, going really straight down, and then W2 at the end of W1, and then the match force. Now, force is kind of like our U in this situation. A truck with a gross weight of 30,000 pounds. So that's a force of 30,000 pounds down, so we call that negative 30,000. If we wrote it as a vector, it would be 0, negative 30,000. Because down would be kind of a Y value, vertical value, right? Next, we're parked on a slope of 8 degrees. Now, to calculate 8 degrees, we've got W1 here. We're going to call that a composition of our cosine and sine, right? So this is our horizontal movement is cosine 8 degrees, vertical movement is sine of 8 degrees. And now we're going to do the projection of F onto W1 from that. So projection. So that's going to be the dot product of those two. And then we're going to do them over the, then spell the formula, what we're doing. So multiplying here, 0 times cosine of 8, 0, plus negative 30,000 times sine of 8, that'll be like our big number here, all over cosine of 8 squared, square of 8 degrees, plus sine squared of 8 degrees. Cosine squared plus sine squared, looks like 80, of 8. That's going to be 1. So basically our answer is going to be this chunk over 1, or that chunk over 1. The negative 30,000 sine of 8 degrees gives us 4,175.193 pounds, and it's negative. Okay, so that's the force that is pulling down. This is how many pounds are pulling down the slope. Okay, that's kind of our, that's one of our pieces. Sorry, kind of weird that we have two W1s here, because technically our projection usually is our W1. Okay, but since this is negative 4,175, the force required to keep us from rolling down the hill is going to be that same value, but positive. So our answer here is going to be 4,175.193. To keep us still, we need that much force going up. Now we have a right triangle here. We've got W1, right angle, W2, and F. We have two of those already. To find the third, we just need to, probably box the correct answer here. We just need to do Pythagorean theorem, right? Find the force perpendicular to the hill. W2 is going to be the square root of that 30,000. Since there's a triangle here, we're assuming this 30,000. If it's negative, it would cancel anyway. Minus, this was one of the legs, 4,175.193, square all under square root. Calculating, I get 29,708.042 pounds. And that is the answer for that. Next, it's a little bit easier when we talk about the definition of work. The work W done by a constant force F as its point of application moves along the vector PQ is given by either the following. W equals projection of PQ on F times the magnitude of PQ, or dot product is W equals force, the dot product of the force and the vector PQ. So what we're going to use, we're actually going to use this bottom form, which is solved literally from the top form, cosine of theta times the force vector magnitude times the magnitude of PQ. So what does it look like in a problem? To close the barn door, a person pulls on a rope the constant force, F force of 50 pounds at a constant angle of 60 degrees, there's our angle, as shown in the figure. Find the work done in removing the door 12 feet. There's PQ. So we're just going to insert those numbers into cosine of theta, 60 degrees, times 50. Our vector is technically 0. For force, 0.50, right? Pounds coming down, right? And we're sliding it across 12 feet is this PQ. So that would be probably 12, 0. So we're going to the right, 12, 0, up or down. So you're just multiplying this. We basically get 600 cosine of 60. Sorry, it's just 60, not 60 squared. And that becomes half times 50 times 12, which is half of 600 is 300 and the label is foot-pounds. So we'll wrap up today's lesson.